The entire center of the Pacific Ocean is a whale.
One big whale.
That's around it.
Yeah. That doesn't change anything for some of them.
That could be a solution, actually, to all of these big whaling issues.
Oh yeah.
Yeah.
Just a big fence to keep everybody out.
Yeah, just raise, well, no, raise your own whales.
Oh, raise your own whales.
Yeah.
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 So I'm surprised that, like, it sounds ridiculous, but I'm sort of surprised that no one's tried it before.
Right?
All right. I think this is it's a couple of minutes past 9. I'm gonna start. So today we'll be talking about models with movement. I think this is the last thing we want to cover in this course, and next Tuesday Jim is gonna do an overview of this course. And I think starting from Thursday, we'll do the presentations. I think so, unless Jim come up with something else to talk about on Tuesday. Well, so movement. So dispersal and migration are very important ecological processes in a wide array of taxa in terrestrial and aquatic system. And I think the role of movement pattern in marine environments particularly critical because majority of marine species have a mobile phase at some stage of their life history. So movement is usually triggered by external stimuli such as chemical, temperature signals, food, population density gradients. So we can always think about modeling movement sort of in 2 different ways, implicitly or explicitly. Okay, so I think the spatial Gumpos model we have done sort of implicitly account for movement within the model because that spatial random effect basically accounts for any unmodeled spatial processes, including movement. So the movement, so the model is flexible enough to estimate a spatial pattern where you have a spiking abundance in some areas and how that changes spatially in the subsequent time period. But it doesn't have the mechanism to model, to explicitly model the movement processes, just able to recreate whatever resulting spatial pattern. So if your data has very strong movement signal, you will estimate abundance at a density, and then you look at density plot over time, you can say that's movement, but sort of visually interpret it as movement. But we can always model the movement process explicitly by putting some movement functions into the model. So if we want to model the movement explicitly, we have to think about what type of movement you want to model and how to do that. That's basically what we are going to talk about today. So the goals of today is to understand the theory of vective diffuse movement models and how to specify a sparse vective diffusive movement matrix. Okay. So here we have several different types of movement, as you can see in this cartoon. So the first one is basically no movement. You have a bunch of sides. So each black circle, it's a you can think of as a spatial location. So we got a whole bunch of locations, and then individuals at each location, they just stay in that location. They don't move. And we also have this kind of this what we call real car movement. Sometimes used to model salmon, where you can think about within a month or so, those individuals move to the next location downstream until they got the destination. And this partial migration is kind of where the individuals want to go a long distance, but when they run out of energy, they just stay at where they are, where they end up. And the last one is diffusion. Is basically you can see there's a certain probability individuals stay at each location, and then there's also another probability they move downstream or upstream. Okay. Well, any questions about these different forms of movement? So I think next step is we wanted to put these movement forms in terms of calculus notation. Okay. So here we have an equation here, dB over dt, which is we can let's say B it's the biomass. It's a vector representing the biomass at different locations. In this case, we have 5 by 5 matrix. We have 5 sites. As you can see, this cartoon we have 5 different spatial locations. So B is a vector of length 5, representing the biomass at each site, and dB over dt is just a biomass over time, and then it's equal to this capital M representing the movement matrix. Okay, so we want to think about as an instantaneous movement rate. Okay, in this case, just within a very short time period, what proportion of the biomass, the change. Okay. So in this case, since we don't have any movement, this movement matrix, I also have to think through this one. So basically, each row is representing different destination location, and each column is the original location. So let's say if we look at the first column, it's basically a set of probability or proportion of say what's the probability or what's the proportion of the individuals at location at site 1 move to other sites. Doesn't that make sense? And the column 2 and so on, the column 2 is the set of probability of individuals at site 2 move to the other side. Okay, since we don't have movement in this case, they just stay at their own sites. So we have a diagonal. We have ones in the diagonal. Any questions about this movement matrix? Okay. Now let's see the example of real car. So for given time unit, individuals at each side move to the downstream side. Okay. And now let's look at the first column again. So basically, over a given time period, 100% of individuals at site 1 move to site 2. Okay. And another important thing is that these columns sum to 1, right? Because you want a proportional probability sum to 1. And then for location 5, it's sort of like boundary location. There's no further site to go, so they pretty much 100% stayed in site 5.
So the equation at the top is just the change in biomass is equal to the biomass times the M matrix?
Yes, exactly. And in this case, the M matrix is a 5 by 5 matrix. And we want to interpret the M as the instantaneous movement rate.
Sorry, you want to interpret what?
We want to interpret this M matrix as the instantaneous movement rate. So for this partial migration, well, again, the same thing. We have so now we have a certain portion of probability indicated by B. That so in this case, the proportion of individuals stay at site one after after a time period is 1 minus P, and then P is just the proportion of individuals moved to site two. If we look at the first column, the same thing for the others. Right. Yeah, so this is the cartoon for the diffusion. So as I just mentioned, there's a certain probability individuals stay at their own site, and there's also a certain probability they move downstream or upstream. Sort of. So now in this case, if we look at column two, so the proportion of individuals stay at their own site is 1 minus 2p, and sort of equal probability to go upstream or downstream. So any ideas on the constraint on the p-value here? Yeah, correct. So because each column has sum to 1. And previously, these p values just range from 0 to 1. And in this case, it has to be less than 0.5.
So if you were to expand this and move from, say, site one to site three,
Mm-hmm.
then you would have the third row would be P, P1.
Well, yeah, as I just mentioned, we want to interpret this a matrix as instantaneous mixing rate. So it does make sense. Like it makes sense intuitively. Um, for any instant, the individual just move to the neighbor. But over a long time period, it can move to like site 3, site 4, or 5.
Right.
Yeah.
But that would be another time period.
Mm-hmm.
Okay.
Yeah, we'll get to that. I think later in the slides, if I remember correctly. Yeah, exactly. That's what we're gonna do in this slide. So basically, what we want to do is to solve this differential equation. This one, the dv over dt, and then we can think this dt as a well, in this case, let's say the biomass at time t, and the alpha is the let's say it's population growth rate. Okay. Well, people in fisheries should be very familiar with this exponential like mortality equation. So basically, the solution uh, to this differential equation is just as this one. So a bt plus a given some time interval delta t. Well, we can calculate as the initial state bt times exponential alpha times delta t. Essentially, this is the definition of exponential function. Yeah. Well, I think we do this because in most of case we in the model we used we basically we use the discrete time interval. So, for example, like year 1, 2, 3, 5. So we wanna we wanted to know after a year what's the corresponding movement matrix. Okay. Let's say we know the instantaneous movement matrix, and then what's going to be the corresponding movement matrix after a year. That's basically uh, how we do this. So in this case, it's just a univariate differential equation. So we have BT. It's not a vector here. Okay. And now, if we have a matrix, as we have seen in the previous slides, it's the M matrix, okay, representing the movement matrix. So we want to solve this multivariate like differential equation. So the idea is that if this A matrix is diagonal, and then it would be easy to just take these diagonals and exponentiate them, and then you will get the solution. Well, in this case, we can think about this. BT is a vector. Okay, let's say we have 5 different locations. So BT is a vector of the biomass at these 5 locations, and then we want to calculate. We want to figure out after some time interval what's the operating size, and then alpha is the growth rate, operating growth rate. So it makes sense if there's no movement. You want to calculate the population size after some time interval. You just take the biomass at each location and exponentiate that. Okay, does that make sense? So what if the matrix, the A matrix is not a diagonal? Well, if A matrix is what we call diagonalizable, and then we can do this math. Well, you have a new A matrix, A prime. Well, you have a transformation matrix which get the A prime to be being a diagonal, and then we can apply the same thing to we can also take the diagonals of this. Let me see. Take the diagonals and exponentiate them.
Why wouldn't they be diagonal?
Well, let's say if you have a that is not diagonal. You mean, but it's diagonalizable, and then you can apply this metric to.
And how do you determine that it's diagonalizable? We're gonna see that later. I mean, how do you determine that A can be transformed into a star that is diagonal?
Yeah, that's well. Well, I think the way they do this is some sort of like eigen decomposition thing. I don't have I can't remember exactly under what conditions it's diagonalizable. But
Let's say most of the matrices are diagonalizable. It's in
Uh,
these cases you have a matrix. It has a high chance to be diagonalized. Yeah, well, we turn into a diagonal.
mm-hmm. Well, John, any ideas, John?
Sorry, I didn't quite catch it.
Oh no, I was wondering. So first, how do you determine that A will be diagonalizable? And if there are no, if there's no real test to determine that, is it the case that most of the matrices can be transformed into a diagonal matrix?
According to Math Stack Exchange, a matrix is diagonalizable if and only if for each eigenvalue, the dimension of the eigenspace is equal to the multiplicity of the eigenvalue.
Yeah.
So, so if you find a matrix with distinct eigenvalues, you should quickly identify those as diagonalizable. So if it has,
Doesn't have multiple
yeah,
same
if it has
eigenvalues,
all distinct eigenvalues,
which
which just means that
it's if you're making, I think generally if you're sort of making like a transition matrix like this that's based in some sort of real physics, you should be pretty safe. It's generally going to be diagonalizable because it won't be like singular or have other problems like that.
So it's related to the rank of the matrix, right? It has to be full rank.
It is. I think it definitely has to be full rank.
Yeah.
Well, thanks. Let's just move on.
Yeah.
Yeah.
There's,
I have a slightly more fundamental question: is why A wouldn't be diagonal in the first place? Because if you're assuming that it's instantaneous movement, and you can only go to an adjacent cell, theoretically we're not wizards, so we don't operate.
Well, in this
why
case,
wouldn't it be diagonal? Like, what would be an example of a case where it wouldn't be diagonal?
well,
it's diagonal in this case only if there's no movement. So in this case, in this diffusion case, you see it's not diagonal.
you can think of those off diagonal elements as rings.
Okay.
Yeah.
Also, so like that's p per second or whatever, p per 0 time.
Okay.
And then, but if you actually say over a second how many are going to move to the adjacent cell, that's some real amount of movement between cells over some finite amount of time.
Yeah.
Like obviously nobody moves in 0 time, like you said, but
Right.
over some amount of time, which is what we're looking at here.
Okay.
You will get some.
And also, if you have a like super fine like spatial scale, and then you have values in this you have non-zeros as well. Okay. So the general solution to this to solve this equation is this operator, what we call like matrix exponential operator. It's basically you can think if you can think if it's like univariate, you just e to the a times the delta t, and then if a is a matrix, and then you use this matrix exponential operator. Okay. Well, I think this slide is where we get to the advection and diffusion movement. Does anybody want to describe what are advection and diffusion?
Advection is sort of a directed movement,
Mm-hmm.
and diffusion is sort of gradient. So you go from, things tend to move from high concentration to lower, out to lower concentrations.
Yeah. So advection is as John said, it's directed movement of individuals in a specific direction. Yeah. So for example, if you have you have a water that goes through a pipe, that's basically advection. And then if you look at very fine spatial scale, you have some kind of chemical traces you put into the water, and how that spread out. Sort of, they have like equal probability to spread out, and then that's diffusion. So diffusion is basically random movement of individuals away from their current location. So what we want to do is basically to figure it out or to come up with a matrix which represents the net effect of advection and diffusion. Okay. I think we'll get to that in a second. Yeah, now that's the more closer to the advection, sometimes called convection. So now let's say we have 5 locations here. We're gonna think entirely about this focal cell in the middle, which is shaded in blue. That has 4 neighbors, 1, 2, 3, 4. Okay. So individuals can only like go to the adjacent cell, cannot go to a diagonal cell. Okay. And then if we have a vector field, in this case, it's indicated by the this green. So let's say so this basically it's how it's the vector field basically affecting individuals, in this case the east. Okay, and then we can calculate the movement matrix as a product, cross product of 2 vectors. The vector, this v vector is the movement vector, and then this s it's a the side the side vector. In this case, the side is pointing to the north. And then I think in this case, the result of this cross product, it's I think it's a scalar in this case. So I don't know if you guys have taken physics, but basically the cross product, if I remember correctly, just using some right-hand rules or something like that. Yeah, so any questions? So this v is a vector, that's the movement vector, and this s is the side vector, in this case pointing to the north. And then the cross product to give you the movement matrix. Okay. So in this case, if we look at the s vector and the v vector, those are perpendicular to each other, and then you got I think you got the maximum cross product. So if you take the vectors of the side, this side, which are parallel to each other. And then the cross product is 0. So basically, the vector only happens in this direction, the east. Okay. So now let's look at the diffusion. Again, we have 5 different locations. We look at the cell in the middle, and then we have a vector of size, S1, S2, S3, S4. And then the diffusion the diffusion is always symmetric, but you can have different diffusion, north, south, or versus, or west, east. Okay. In this case, as indicated by this red arrow, we can see we have the diffusion north, south is higher than west, east. Okay. So basically, what we do is just to bookkeeping things. We keep checking each direction, as we have seen in the previous slides. So basically, it's the same way as we do a vector. Let's see. Yeah. So in this case, we can see the movement matrix. It's just a summation of these four terms representing 4 different directions, and we just so F1, the cross product of F1 and S1 is representing this direction, and F2 and S2. Right? Yeah, that's and then if we want to consider advection and diffusion, at the same time, what we do is just stack these vectors together. We could just stack all the vectors. In this case, we have diffusion and advection happens simultaneously. And now you see those movement vectors, M1, M2, M3. So M1 is basically what you have for diffusion plus the advection. And then again, we just sum these terms to get the movement matrix. Any questions about this advection and diffusion?
Are those cross products or dot products?
I think it's cross product because I think you have to use the angle between these two vectors,
right,
to get you the cross product. As I just said, if those two are perpendicular, and then you have, I think it's 1, and then you have the maximum cross product. If they are parallel, and then it's 0. But I think in this case, I think generally, if you do a cross product, you get the result is a vector, right?
the result.
But in this case, I think the result is it's a scalar.
So the dot product of these two vectors will give you a scalar, which I think is what you want, because ddt should be a scalar.
Yeah.
And the cross product of these two will give you a matrix. So because it's like M1 times S2 instead of, so you go at 2 by 1
Mm-hmm.
times a 1 by 2 gives you a 2 by 2 matrix if you do a cross product, versus a 1 by 2 by a 2 by 1 gives you a scalar or a dot product. And the dot product gives you the sort of length. Geometrically, you're sort of getting the projection of the length of your drift vector, your M,
Mm-hmm.
onto your side, which sort of gives you, if they were at an angle, then you would expect that this is going to give you the full movement across this border.
Yep.
But this will give you less because it's at an angle.
Right.
So that's what the dot product gives
Well, yeah. Let me think about that later more. Yeah. I think anyway. This result of this product should be a scalar in this case. Yeah. So if we want to write out the equation, mathematical equation for the convection and diffusion movement, usually people use this equation. Well, this whole term is just the movement matrix. The left-hand side thing is the convection term, and this one is the diffusion term. I think this is a gradient operator.
Sorry, what's the red triangle?
This upside down triangle.
Yeah.
I think it's gradient operator or something like that. Yeah. So what it cares more is we wanna get we wanna do the matrix exponential for this whole term, which will give us the movement matrix after a certain time period. Okay. So this whole term is interpreted as the instantaneous movement matrix. And then what we want to do is, because this matrix exponential operator is very computational, expensive. Okay, let's imagine you have hundreds of thousands different locations, and the matrix is going to be huge. And then this operation is very computational expensive. And what we do is use Euler approximation. So this is a equation for the approximation. The capital I here is just the identity matrix, and plus this whole term is the instantaneous movement matrix divided by the number of time steps. Okay. So let's say we want to calculate. Let's say we know this instantaneous movement matrix, and then we wanted to calculate what's the corresponding movement matrix after a year, and then we want to do during a year we want to do 3 steps, and then in this case the n delta t equals to 3, and you just do this approximation 3 times. Will get you the annual movement matrix. So this is another illustration of the Euler approximation. So the reason we want to do this approximation is mainly because the computation issues. Okay? We know that we can gain computational speed by taking advantage of sparse matrix. And this approximation will get us the sparse matrix. So now in this case, we have like 25 different sites. It's a 5 by 5 grid. Okay. And then if you do a matrix exponential operation, you get this matrix. It's a dense matrix. Okay. So I think in this case, the color represents the red color is high values, and the thing white is zeros. And then if you do all your approximation with number of time step is equals to 1, you get this matrix. You get this movement matrix. In this case, it's basically treating, I think it's treating the instantaneous movement rate as the annual movement rate. Does that make sense? So basically, in this case, after a year, individuals that are given size only go to the neighbors. That's why you see this score. And then as the number of time step, as the number of steps increase, the approximation approach the matrix exponential operation eventually. Okay. So in this case, if you do the approximation with number of steps being 10, and then it's pretty much the same. It's basically identical to the matrix, to the result of matrix exponential operation.
So does that mean it's faster to do a 1-step increment 10 times than to do a 10-step increment 1 time?
Well, if you look at this equation, I think we specify the number of time step here. So basically, it's one time, but within one time within this approximation, you do 10 times. Doesn't that make sense? I guess.
Yes, I don't know. I guess still just sort of not sure where this is going to go, but you could use that 1-step transition matrix, the sparse one, and apply it like 10 times to get a 10-step transition, or you could calculate your 10-step transition matrix, which is less dense, and apply it to get.
But then you're using a linear approximation, essentially using a linear approximation to your exponential at every step instead of more closely approximating to exponential. So you lose accuracy. So basically, if you specify just one steps, and then it's treating the instantaneous movement rate as the annual movement rate. Okay, so after a year, you basically individuals can only go to the neighbors. Well, if in this case, if a step is 2, and then after a year, those individuals can go to the sales can go to the sales net 2 sales away. Okay. Yeah, I think that's basically pretty much about the math we want to go through. So this is a spatial gunpowder model with movement.
Yeah, so this term should look familiar, which is something we have done. So we just this whole term, it's the spatial compass model without movement. Okay? And then the t plus 1 is the abundance of biomass at time t plus 1 equals to the biomass at time t. So the transition between like time t and time t plus 1, the first thing happened is the movement. So as we can see here, we have movement matrix m times dt, and then the right hand side is the Gauss component. So we've seen this before. So if the movement matrix is an identity matrix, you just reduce to a version with no movement. Yeah. So this slide. Yeah. So we have talked about two different ways to do the parameterization for the Gampus model. Right? So what are the difference between those two? So basically, in this case, the state space parameterization, we are treating the density as random effect. Because it turns out in some cases, this parameterization is faster. Well, I think this is an example of the movement matrix. So again, just to summarize, it's if we do the Euler approximation, we'll be able to get a sparse matrix. It's easier for computation, and it takes less computer memory, and it's just it has faster speed. Okay, so for example, in this figure, you can see it's pretty sparse. I think in this case, maybe they have 100 size over 25 years.
Can you on that last slide, can you say why space is faster?
It's not always faster. I think it's case specific. Well, yeah. Yeah, that's why we always try different like parameterization, different ways to parameterize a model and figure out which one is faster. Yeah, so this is an example of the simulation. So in this case, we simulate 20 years of, I Technically, in this case, it's diffusion. You can kind of see, like in year 12, we have a high density here, and over time, how that diffuse out over time. Maybe also in year 18, you can see how that density changes spatially. And then we use like 200 triangles to approximate this spatial process. And we can see we pretty much recover the two spatial pattern. And it only took like 5 minutes on the laptop. It's pretty fast. So here is a example of diffusion. So you start from year 1, which has a high density, and then how you spread out over time. And again, we use triangles to approximate or represent this process, and you can see how it changes over time. Yeah. Yeah, that's pretty much about the lecture. And we can go to the code. So does anybody doing movement for the final project? I don't think so. Yeah. So this one is using a package called movement tools, which should be on the GitHub. But unfortunately, this package it's not. I don't think it's well documented. So a lot of functions.
Has it been published?
Yeah, it's a public available. I think at some point it's I think it's a result of a paper or something. But yeah. So yeah, this I already have that package installed. So I'm just go ahead and run this block of code. So basically, what this code does is we specify how many the number of samples, and I think we made a 50 by 100 grids, and then we simulate the data on a grid, and we can also specify the spatial domain in terms of whether it's grid based or mesh based. We can this dynamic models we can switch between Gunpers or Ricker model, and in this case we have 20 years simulated 20 years data. Let's see. So this let's see what this gives us. Yeah, this log G it's the grids, and log S it's the location for sampling. It's a sample location. So for example, let's make movement mesh. It's a function building that movement tool packages. So I don't know what exactly it does, but it turns out this returns the movement matrix. That's the mesh list. Mesh list. Yeah, I'm trying to figure out where the movement matrix. Let's see. Getting okay. Yeah, let's look at this figure first. So we randomly select a whole bunch of locations, sampling locations, and we created the mesh to match the sampling locations well, like we did for SPDE method. That's the plot for that. Where's the movement matrix? And here Jim has two different ways to simulate in terms of the simulation domain. One is mesh-based, the other one is grid-based. I think in this case we're gonna use the mesh-based because on the TMB side in the estimation model we use the mesh-based. So in this case, there's no like model specification, and it takes a while to run a model if we use the grid-based.
Because it's misspecified or because it doesn't do grid as well?
Well, I think part of it is because misspecified, and also I think grid has more. It's finer in terms of spatial scale.
Or is it also that you can use sparseness with mesh and you can with grid for the in terms of your spatial domain?
No. You can also use sparse matrix for grid. Yeah. Well, I'm trying to figure out where's the movement matrix because that's an important thing. Well, I believe it should be somewhere in the mesh list. I don't see. Maybe. Sorry, it should. Yeah, I think it's a. No, I don't think so. Yeah, because the movement matrix is it's the thing I wanna talk about. It should be in a move. Yeah. It's in a move list. Yeah. Right. So let's see. All right. So in this move list, we have four matrices. I think I should really write it out. Yeah. Let me find that slide. So as I mentioned before, the way we model this movement is that we want to come up with a matrix A that represents the net effect of advection and diffusion. So the way we do this is, let's say I'm gonna just write it out. Well, bear with me. B equals is movement matrix A, right? Well, you have a delta T. So how we calculate this movement A matrix is that we have, well, let me see. In this R case, we have four different matrices: M1, M2, M3, M4. So we have M0. So let's say it represents the north. And then there should be a parameter here. Let's say lambda 1. And plus lambda 2 M south. Well, it's very hard to write it out this way. And plus lambda 3 plus lambda 4. All right. So this movement matrix is basically calculated as a combination of four different matrices representing four different directions. And then we can estimate, well, we have parameters for each of with four matrices, lambda 1, 2, 3, and 4. And then we can estimate those lambdas. That's how we come up with the movement matrix, A matrix. So what happened what happens if all these lambdas are equal? Like those lambda 1, 2, 3, and 4, they have the same value. Then it's diffusive movement, right? And then it's diffusive movement. Okay. Then I'm gonna just go ahead and run a model. Well, it might take a while to finish. Yeah, while we're running the R code, we can look at the CPP file. Make it bigger. Well, I think a lot of this look familiar. Okay. Except in this case, yeah, we have like we pass the CPP, these 4 matrices. I just mentioned representing different movement towards different direction. And then the 3 matrices, the SPDE matrices, those are the fixed effect parameters. And in this case, we use the stage-based parameterization. As you can see, that log UGT, I think it's log density, which is treated as random effect. Yes. And then this whole block of code is something new. So yeah, in this case we have options. There's option vectors allows us to specify whether if we want movement or not. Okay, so if there's no movement, the M sparse matrix is just a identity matrix. And then if there's a movement happening, we use the Euler approximation. As you can see, the line on 83. Let's see.
So here we see like the lambda 1 times n1 plus lambda 2 times n2 and so on. But then you divide this sum by something. So what is this?
Which one? The
The
82?
MD spares.
Oh, this is the approximation.
Oh, okay.
Yeah, so this gives you the instantaneous movement matrix, and then we use the approximation or approximation to get the. In this case, I think the annual movement matrix.
What's MT do?
I think that's the number of steps using the approximation. Let me see. Yeah.
Plus an identity spares matrix. That's what it is.
Yeah. I believe somewhere later in the code there's oh yeah, right here. So line 112 and 114. It's how we do the order approximation. So you specify the number of steps, and then you just do this approximation over, and this and keep if it's 2, and then just do it twice. Okay. What? So I think so in the state-based parameterization case scenario, in this case, RT is a density, and log GT is a density in log space, and then we take an exponential, and then that's the and then we have the U prediction. That's a predicted density, and then we apply the movement to get out the prediction. And there's a switch where you can switch between models, whether it's a Gumpus or Rigor model. And then we take that difference right here, line 124. That's the epsilon in this case. Let me find the slides here. So line 124, the difference between those two objects, two variables, it's the epsilon in this case.
And that's like the process error.
Yeah, that's the process error account for like spatial processes that model spatial processes. Yeah. Yeah. All right. And then we can look at the results. So we have the estimated values for these parameters, and also the true values are listed here as well. So rho, I think, is the parameter controls the density dependence in a Gumpus model. The true value is 0.5. In this case, it's close. And then sigma u and sigma o, and this range parameter is the decorrelation distance, I think, really. So these four parameters are pretty close to the true values. And M back 1, 2, 3, 4. It's this correspond to this lambda 1, 2, lambda 3, and 4. Okay. So it's slightly off. In this case, it's estimated 0.8, 0.86. matrix, the true values is 1. I think in this particular case, we specify these 4 values being equal. So basically, it's like diffusion process. Yeah. I believe there's a switch that you can control the movement type. Yeah. So include movement. If it's 0, it's no movement. If it's 1, and then it's just stationary diffusion, as we see here. Those values are the same. And if it's 2, and then we have independent direction movement. Okay. Just go ahead a second. Let's see. This one should give us the comparison between movement matrices. So this is a true movement matrix that we simulated. And then we can look at the estimated movement matrix. Well, I should have plot these two in the same figure. Well, anyway, it's pretty close. It's
What object is the movement matrix?
this one.
That's the estimated movement matrix.
Estimated is this A matrix.
Yeah, I guess, and you're comparing, you want to compare that to the simulated?
Yeah.
To the movement matrix used in simulation?
Yeah. So if we look at the those parameters, so we use 1 for this for these 4 parameters, and those are the estimated values. Then if so you see the lambdas in this case. In a simulation, we use 1, and it turns out the model estimates those values being 0.8. Yeah. Yeah, that's pretty much I have for today. Any questions? Yeah.
Yeah, I have a question. It's not related really to the course. It's more general.
Mm-hmm.
I've always wondered why we always use a random seed at the beginning of each code, like the set seed option.
Mm-hmm.
This I've never really understood the rationale.
Well, obviously you can get the same result over time. Next time you run it, you get the same result. It's you can replicate. Doesn't that make sense?
So it's a guarantee that when you simulate some random stuff,
Yeah.
Not sure.
Could it work when you generate from out of nowhere?
It helps with like debugging because if you're like running the same kind of code, you're getting like the same random values each
Yep.
time, and so then you can like figure out like where your problem is coming from because you want to like keep the random things you're generating the same or something like that. Or if like I share my code with you and you want to make sure yours is running right, if I set a seed and we both run it, we'll get the same exact answers. Whereas if we didn't have the seed, we might get just sort of close things. Right?
Yep.
Although like in these kinds of situations, like there's randomness in R that we're setting the set seed, but then I don't know how much there's also randomness in the like TMB optimizer stuff, but I don't know how much of that matters.
Well, as long as you input data are the same, you'll get the same result.
I don't think there's anything.
There's no randomness.
No. It's a deterministic.
Yeah.
The only place you get different results, I think, would be rounding errors if you're on a 32-bit versus a 64-bit machine or something weird and sort of obscure like that.
Right.
That you'd expect to get exactly the same.
It's not like a MCMC sampler, right?
Exactly. Yeah.
I have a question about like simulating the random effects, the spatial and temporal random effects.
Yep.
Mostly just because whatever Jim is using always gives a warning message. And so I'm wondering, like, he just like sort of uses that and that is like his way, and I just sort of wonder if that's like how everyone does it. Also, this is only like assumes a specific correlation type, right, function when we do it, when we use the RM Gauss. Right, this is like, is this assuming, I guess it depends on what our scale is, or it just is like a return?
It's a squared exponential.
Oh, okay.
So it's, yes.
And so that is sort of like the most like unconstrained?
No, it's the most smooth. So it has infinite squared, infinitely mean square differential, or whatever that, not that I know exactly what that means, but
Right.
It's a fairly constrained. I mean, you're going to make basically you're generally going to make an assumption about how smooth your field is. That's pretty hard to get around that. So this happens to be super duper smooth. And you can specify it to make it less smooth. That's the main assumption that we yes.
Yeah.
It's like a common thing to do.
Yes. Yeah. I feel like I see people do exponential maybe a little bit more often. But that's sort of the opposite extreme where it's a zero derivatives. Right.
So when we're fitting this model, what correlation structure do we assume? Like that.
So on the TMB side, we always use the return function because we use SPDE, which that's basically where it comes from.
I think we usually use the SPDE with alpha equals 2, which in 2 dimensions means that mu is 1. So it's has one derivative. So it's smoother than an exponential is going to turn 1/2 with 0 derivatives. But we're sort of generally we're fitting it with assuming a single derivative and then what we're simulating from infinite derivatives. But we're also not.
Yeah, based on my experience with the girls, I think it's pretty flexible function where you can. I think there's two argument. You can two parameters you can control, like the correlation distance and the variation. So basically, it can get you. Basically, I think in most cases, basically like whatever like spatial pattern you want to have. Yeah. Well, if there's no like final questions, I guess we can call it. Yeah.